this problem is a little bit more of a challenge. We have a wire which is bent in the shape of a semicircle. The semicircle has radius capital R. The whole thing has current I. Let's say that the current is flowing around the loop this way. Let's put our I in there. The circuit lies in the XY plane and a uniform magnetic field points along the positive Y-axis, so the magnetic field is up. Find the magnetic force on the straight portion of the wire and also on the curved portion of the wire. Let's do the straight part first. That's kind of the easier part. So on the straight part, the magnetic force, FB, let's do magnitude and direction because the right-hand rule part is going to be pretty easy. So it has a magnitude of I times L times B times the sine of the angle between the length and the magnetic field. That's going to be 90 degrees. So I times L times B. Only trick here is what is L? So the length of the wire here is a radius and a radius. So 2 times the radius. So there's the length of that wire. I times 2R times B. To get the direction, let's do our right-hand rule. So our force equals IL cross B. I'm just going to shift my paper to make it a little easier to do. So I is the thumb, B is the force, F is our middle finger. So our force is coming up out of the page, so that's the direction of the force, in the K direction or out of the page. So we'll call this one a vector, and the direction is out of the page. So there's the force on the straight part of the wire. Next, we'll find the force on the curved part of the wire. So we want to find the magnitude of the force again. So the magnitude of the force, let's start with that part, is the magnitude of IL cross B. This one's a little bit different. This one's a little bit harder to do because the length is not straight the way it is here. The length is actually a curve. This is on an arc, so we've got to do an integral over the length. So that's going to be the integral of I times ds cross B. So that's what makes this one a Jedi problem, is the fact that we have a curved wire, so we can't think about it being straight. We have to do the integral over the length and add up each little bit of force as it goes. So that's our absolute value signs outside. We can put them on the ds cross B. So the magnitude of ds cross B is equal to I times ds times B times sine theta. So now, why don't we talk about what is ds, what is b, what is theta? Let's see if we can figure that out. So ds is a little bit of our wire, a little bit along that path. And the direction is the same direction as the current flow, so there's our ds. Let's think about our angles that we have here. So we'll go from the center to our ds. And this is going to be an angle theta. So the angle between ds and b is going to be theta. And that's just from doing a little bit of geometry. So our ds is this way, b is this way, so the angle between those two guys is theta. So let's remember, how can we write our ds if we have things in a curve? Well, ds equals, since s is equal to r times theta, then ds is r times d theta, where r is the radius. So let's put that guy in there. I times the integral of r times d theta times b times sine theta. We can take our constants out front, so I, r, and b are constants. So we've got the integral sine theta d theta. We ask, what are the limits of the integral? Well, we have to go from the start to the finish. Our beginning ds is down here at the bottom. That's where theta equals 0. Our final ds is after we've come all the way around the loop, and that's where theta is equal to pi. So there's the limits of our integral. The integral of sine theta is cosine. It's going to be evaluated at pi and 0. So we have I times r times b, sort of cosine pi minus cosine of 0. Cosine, oh, dropped to negative sign. Integral of sine is minus cosine. So we have minus cosine minus a minus cos of 0. There we go. Cosine of pi is minus 1. Cosine of 0 is 1. So minus a minus 1 minus minus 1 gives us 2. So 2 times r, 2 times I times r times b for the magnitude of our force. Let's get our direction. We can use our right-hand rule. So our length goes in this direction, our magnetic field goes in this direction, and our B goes into the page. And that's true no matter which DS we took. So if we look here, it goes like this. If we go here, it goes like this. If we go here, it goes like this. So no matter where we are on that curve, we get into the page. So FB, so we'll just put into the page here. Into the page is the negative K direction, so we get -2 times I times R times B times K. So the magnetic force on the curved part is equal and opposite the magnetic force on the straight part, which makes sense because we expect that the net force on that closed loop is going to be 0. So we do get an answer we expect.